Today we're looking at lesson 6.1. This will be the first lesson of our new unit on transformations and symmetry. So we're starting on geometry today. And today's objective is, given a pre-image and its image, I can name the rigid transformation in 2 out of 2 problems. We're going to talk about what those terms mean: pre-image, image, and a rigid transformation. So first of all, Pixar. Have you ever seen a movie, any of these movies up on the screen? Can you recognize any of these characters? So Pixar does animation, and there's actually a lot of math involved in that. And we have a video from somebody who works at Pixar, and I can't record that again because there are copyright issues, but I will link to that video, and I recommend you just click on it. You only need to watch the first couple of minutes, and it will introduce you to some of the transformations we're going to be doing in this unit and how they are used in the animations they do in Pixar. So some of the transformations he talks about in that video are translations, dilations, and rotations. And the one we're looking at that he didn't cover is reflections. Translations are when you move an object up, down, left, or right. Rotations are when you move an object around a circle, essentially, around a center point. A reflection is like a mirror. You reflect something over the mirror. And then a dilation is when you make something bigger or smaller by a dilation factor. Now in this class, we're actually going to be focusing on only 3 of these, called rigid transformations. We're not going to be looking at dilations. Dilations are for Math 2. So in this unit and in this class, we're going to be focusing on these 3 transformations. And why we call them rigid is because they retain their same size and their same shape no matter what you do to move them around. So when you're thinking about rigid transformations, imagine you're holding one of these blocks, like a tangram. This is what that's called, a tangram. These are blocks that you can use to solve little puzzles, make different pictures. Or if you've ever seen like wood blocks that little kids have, you think about a wood block in a particular shape, and you can't change its shape unless you break it. You can't mold it, you can't make the sides a different length. All you can do is move it through space. You can move it up and down. You can move it left and right. You could flip it over. You could spin it around. You can do all of those things. And at the end of it, all of the angles are still the same. All of the sides are still the same length. These are what we think of as rigid transformations. Anything you do to a wood block would be considered a rigid transformation. So just some notation on transformations. When we transform a shape, it means we've moved it or changed its size. In this class, we'll be focusing on moving it different places. And we have what's called a pre-image and an image, or sometimes this will be called an object and its image. The pre-image is what we're going to transform, and the image is what results after the transformation. And we have this notation that we call prime. This is A prime, and that means where the point went after it was transformed. So A is the beginning point, right here, and then it was transformed and it went over here to A prime. Similar with B and B prime. Now this prime looks a lot like an apostrophe because it is an apostrophe. But there are some fonts, it's a tiny bit different character, but really it just looks like an apostrophe. We call it prime in this context, though, when we're talking about geometric transformations. Look at these 2 shapes. You can see they are rigid. They retain the same shape, the same size. What kind of transformation is this? Can you identify it? We talked about 3, translation, rotation, and reflection. Which one are we looking at here? This one is a rotation. You can tell because this A point was at a different orientation. We rotated it up to be on the top. Similarly, the B rotated over here, the C rotated, and the D rotated like this. So first we're going to talk about translations. We're going to jump into these 3 different transformations a little bit deeper. And translations move left or right, up or down. So you can see in this image right here, we have a polygon. It's defined by its vertices, its points. If we take point B, this one has moved 6 to the right and 1 down, and we get B prime. B prime. If this is a rigid transformation, called a translation, that means that every other point did that same path, 6 right, 1 down. So let's see if A did that. 1, 2, 3, 4, 5, 6 right, 1 down. We get to A prime. That would have to be true of C as well. 1, 2, 3, 4, 5, 6 right, and then 1 down for C prime. So every single one of these points moved 6 right and 1 down, and that makes it a translation. Now, one way we can describe translations is with something called a vector. A vector is essentially a line segment. It has a distance between 2 points, connects 2 points. But the difference between a vector and a line segment is that a vector has direction. So you see there's a little arrow here. That tells us that the vector is this long and it goes in this direction. We talk about vectors more when we study physics. It's very commonly used for something like velocity. Velocity has a magnitude, which we might also call length in this case. A magnitude is like a number we calculate. So 60 miles per hour. So if you think of a car going 60 miles per hour, it will have a direction and a speed. The speed is 60. So we could represent that with a vector, a particular direction, and then the length would be 60 if our units was miles per hour. So similarly, when we're doing transformations, we can use this vector to describe where the transformation goes. You can see this vector goes over 6 and down 1. So it's this direction right here, and it went from the pre-image to the image. So we could use that same vector, we could pick it up and put it on the C, and it would go down to C prime. Pick it up and put it on the E, and it would go down to E prime. So we can describe translations with vectors. And now we're going to look at GeoGebra. Now GeoGebra is a program, it's kind of like Desmos, but we can use it for geometry and moving shapes around in the coordinate plane. So I'll put that link in the video. You can click on this and work along with us. We've got this little lizard animation guy. And we're going to represent this lizard with a very simplified polygon. Now, in real animations, of course, they're going to have lots more points than this. So we've just simplified it down for our purposes. He's going to be represented by these points right here. And that's going to represent, that polygon right there is going to represent our little lizard. And our first task is to translate the lizard so that the tip of its nose lands on the translate point, making it appear to be sunbathing on the rock. So we're going to move the lizard, keep that same orientation, just move the lizard up to this translate point. So here we are in GeoGebra. Here's our little lizard. And the first thing I like to do is give myself a little bit more space to work. So this is a really big area for my tools to be in. I like to just grab this and make it a little bit smaller so I can work over here with more space. And then I'm going to use this move tool quite a lot. I'm going to select that and then I can move my canvas up a little bit so I can see all of these pictures. So our first task is to translate the lizard onto the rock. So how we're going to do that is we're going to go down to more. We're going to do more tools. And there are a whole bunch of tools available in here. We're going to scroll all the way down to the bottom where it has transform. These are the transformations we're going to be looking at in this unit. And the very first one is translate by vector. So I'm going to select that, and you can see it gives me instructions here. Select object to translate, then the vector. So the object is this polygon we've said is going to be the lizard, and I'm going to just click inside of it. And then the vector we're going to have to create ourselves. Now it said take the lizard's nose, right there, lizard's nose, that A point, to the translate point up here. So here we go, A to translate. And now you can see our little simplified representation of the lizard is sunbathing on the rock. Now if I click again, it's going to try to do another translation. I need to click this little purple thing to get back to my move drag tool, or I could select it up in basic tools again. So now I can drag this around. I'm just going to zoom in a little bit so we can focus on what we're looking at here. So if you look really close, you can see that has an arrow. We made a vector from A to A prime. Now if I make a line segment from B to B prime, do you notice anything about those lines? How do those lines relate to each other? Those two lines we just made between A and A prime and B prime. Do you notice anything interesting about them? What if we draw a couple more? Let's do C to C prime and D to D prime. How do these lines relate to each other? If we draw the lines from the pre-image to the image, there we have all the lines drawn. And we can even zoom in a little bit more so we're not distracted by the pictures. So we're looking very closely at these lines. What do you notice about these lines? So these lines are all parallel. They're all going to run in the same direction, the same slope, and they even have the same length, right? Because we said this vector is the same length, so we picked it up and moved it up here. All of these lines have the same slope and the same length. So translations will trace parallel lines for all of their points. So you can play around with this a little bit more. We can go back down to the translate by vector, and we can click on our lizard and move him around other places. Say we want to move his foot down over here. Now we translated him there. Or we can move his front foot up here. So now he's right in that puddle of mud. Or we could move him so that he's sitting right on top of the cactus. We can make all of those translations happen using a vector. So go ahead and play around with that for a minute. You can pause the video and come back when you're done moving the lizard around the coordinate plane. And our next transformation we're going to look at is reflections. This is taking an object with a line and reflecting it over that line. So reflections mirror over a line. You could even think of this line as a literal mirror. So you'd have an image on one side and then you'd see the opposite image on the other side reflected back. And the way we map out reflections is the distance to the line is the same for the pre-image and the image. So you can see here on B, the distance is 1, 2, 3. And the distance to B prime is 1, 2, 3. So if we looked at A and A prime, we'd see 1, 2, and 1, 2. And E and E prime, we have 1, 2, 3, 4, and 1, 2, 3, 4. So all of the points are the same distance away as their image, same distance away from the line. Now we usually reflect over axes. That previous slide we looked at a reflection over the y-axis. But we can also reflect over the x-axis. That'll go up and down. You can see here D is 1 unit away, D prime is 1 unit away, or C is 2, and then C prime is 2. So this would be a reflection over the x-axis. But we can also reflect over any line. It doesn't have to be horizontal or vertical. You'll notice over here we have the line y equals x, and we can reflect over that line as well. If we look at our pre-image up here, we can see C is one diagonal away from the line, and C prime is also one diagonal away. Similarly, D is one diagonal, D prime is one diagonal. Or E is two diagonals, 1, 2, away from the line. E prime is also 1, 2 diagonals away from the line. So any line would have the same distance between the image and the pre-image. So we're going to take a look at this in GeoGebra as well. And now we're going to reflect the lizard over the reflect line. The reflect line is y equals 1/2 x plus 16, and it's graphed for us. And we're going to try to get the lizard to do a backflip over the cactus by reflecting him over the cactus. So here I have a bunch of mess in GeoGebra because we did a whole bunch of translations. You can reload this page, so just press the refresh button. And it might prompt you to reload. You say yes, reload. You could also just click on the link again and that'll open it in a new window. So once again, I'm going to make this piece over here, our toolbar, a little bit smaller, and then I'll move this up. Actually, no, I'm going to keep it down here because I want to see up here as our lizard flips over this cactus. So once again, I'm going to go down to More and Transform. And now we're going to reflect about a line. I'm going to choose that one. It says select the object to reflect, then the line of reflection. So again, we select somewhere inside this polygon, and then we can select the line of reflection. And you can see now the lizard looks like he's doing a backflip over the cactus. His little bottom foot has flipped up. There's his tail. His nose is up here now, A prime. This is his front foot. And all of these distances, A down to the line, or A up to the line rather, and A down to the line, those are the same distance. D up to the line and D prime down to the line. If you'd like, you can also reflect the lizard over other lines. So for instance, we could reflect the lizard over the y-axis. Let's try that. Reflect about line, select the lizard, select the y-axis. And now you can see it's flipped right over the y-axis. If we look at the distance to A, that looks like it is 17 right there, because we're going from 0 up to 17. And if we look at the distance to A prime, that's 0 to negative 17. So the distance here is 17, the distance there is 17. That fits what we know about reflections. Points are the same distance away from the line as their image. We could do this again. We could reflect our little lizard over the x-axis. And again, our distance, say from F to the x-axis, this is 11, right there, 11. And then our distance to F prime is also 11 because it goes down to negative 11. And even one more little piece, we could reflect our lizard over any line we want to create. So if you scroll up a little bit, under lines, you can create a line. It's also under basic tools. You just want to make a line anywhere. Let's see, let's make a line like right here. You can define a line with 2 points. And then let's try reflecting the lizard about that line. So it looks like he's crawling up onto the rock now. You can do that with any line. You can create any line you want, and we can reflect the lizard over it. So that brings us to our third and final transformation, which is rotations. Now rotations rotate around a particular point. So you can see here we started with A A was a particular distance from this middle point here, F. And when we rotate it, it keeps that same distance away from F when it becomes its image. And once again, we rotated it again, and it stayed the same distance away. This distance we know as the radius of a circle. When you take a central fixed point and take, say, like a piece of string and trace around, you get a circle, which is exactly what we're doing here. We're taking this fixed distance, this fixed radius, and tracing this point A around a circle. That would be true of any of these points. So we'd take B, and this would be a bigger circle, but it would go around that same point. B would trace the circle around like that. And we measure rotations by degrees. Now, if you think back on degrees, how many degrees are there in a full circle? There are 360 degrees in a full circle. So when we talk about degrees, what we're talking about is proportions of a circle. You can see we've gone part way around a circle here. We went 120 degrees. And what we mean by that is 120 out of 360. That's the fraction of the circle we went around. And that simplifies to 1/3. So this is 1/3 of a circle, 1/3 of the circle. If we went around that again and one more time, we would get back to the beginning. We'd have a full circle. So rotations are measured by degrees, and also we can go clockwise or counterclockwise. So you can see in this case, we started with A, we went to A prime. This is counterclockwise. But we could also have gone 120 degrees clockwise. That can go this way as well. Remember, a clock looks like this. 12, 1, 2, 3. So clockwise, that's clockwise, goes that way. And then counterclockwise goes backwards with the numbers going down. This is counterclockwise. So we're going to go back to GeoGebra one more time, and we are going to rotate the lizard now. Rotate the lizard 90 degrees about the rotate point, so it looks like it's diving into the puddle of mud. I have this whole mess on GeoGebra again, so I'm going to refresh and get rid of it. Make my toolbar smaller. And now we're going to go, well, actually I'm going to move my canvas first, just so I can see that mud puddle. And I'm going to go down to More. Down under Transform, now we have a Rotate Around point. That's what we're going to use this time. And the instructions it gives us are select object to rotate and the center point, then enter the angle. Okay, so we're going to select the object, select our lizard, select the rotate point, and now it's going to prompt us for an angle. And it said we were going to do 90 degrees on this one. And notice we can choose counterclockwise or clockwise. Now we want the lizard to go this way, right? So that's counterclockwise to get into the puddle of mud. So we're going to leave it listed as counterclockwise, but we could choose clockwise if we wanted to do a different direction. And there you go. The lizard's nose is A prime, so there's the A prime, or the lizard's nose is A, so A prime is now diving into that puddle of mud. We did a rotation on point A around this middle point. Now one thing you'll notice is if we make a circle centered at that rotate point and we put it on A, you'll see we get A prime. A prime is also on that circle because they're the same distance away from the center. They're on that same radius. If I do that with B, you get the same thing. B is on that circle and B prime is on that circle. And they've gone the same angle, which was 90 degrees. 90 degrees there, 90 degrees there. And this is true of all of the points. What we get is concentric circles is what these are called. I put this on the D point, it goes through D prime. Concentric circles just means the same center, which makes sense, right? Because we're making all of these circles from the same center. So when we make rotations, the image points will trace concentric circles. Now you can zoom out and try rotating around whatever point you want. You can rotate lizard around over here, and maybe let's go clockwise and like 100 degrees. You can try whatever you want. You could think about what will maybe happen if we try rotating a lizard around itself. Like if I look at this image up here and I rotate that around a point right in the middle, what'll happen? Let's have it go 45 degrees, sounds great. So it landed right on top of itself. So rotation around a central point, a point inside the object, seems to spin it around on a point right in the middle. So you can play around with those rotations. Rotate the lizard however you want. You could even do multiple in a row and see if you could do different actions with the lizard. GeoGebra is a free tool. You can open it up anytime. You can open up this particular graph, or you can make your own. So it's a great tool for visualizing geometry. So now we have a question. Corresponding points in a translation. We have to think back to translations. We covered those first. Do the corresponding points trace parallel lines or concentric circles? Remember when we drew those vectors from A to A, from B to B? Those made parallel lines. What about rotations? Did rotations make parallel lines or concentric circles? Rotations, we said, went around a central point and went a radius. So corresponding points in a rotation trace concentric circles. And finally, we have the same question for reflections. Now, we didn't talk about this specifically. We didn't trace this out. But you could do it in GeoGebra if you wanted to. You could go make that reflection happen again and trace, put a line segment between A and A prime, B and B prime. But just based on what we talked about, how reflections are defined, they're right the same distance, same straight line distance from a line. Would you guess those make parallel lines or concentric circles? Since they are the same distance away from the line, they make parallel lines. They're not going around a central point. They're straight line distances from a line. So that covers everything today. Given a pre-image and its image, I can name the rigid transformation in 2 out of 2 problems.